everyone, how are we doing this morning? Good to see you here. We got Carter in the chat. We got Cassandra in the chat, Fleming, Madison, Leo, and Carter again. What questions are there? Hey, morning, Carter. A little bit of music right here. Let's put it to live chat. What are people saying? Alea, great to see you here too. Start up MewBot. We have a sick bunny. Been taking care of Jolly this morning. Can we do the canvas content? Supposed to probability of the bus arriving on time is 0.4. What the? Yeah, let's do that right here. Let's go grab it. And let's drop it in. I'm trying to help Jolly fit him some stuff. Waist size question next. You bet. Let's do it right here. So, canvas content, at least 1 buses. Okay, and then waist size, chapter 14. Waist size question. And stat 201 taken down. Ask the question. We got it. Jolly, like I think it's I can't never spell his name. I don't know how to spell my bunny's name. Maybe he's mad at me about that. Sampling distribution. Which one do you want to do, Cassandra? Can we do the filter the data? 4A. 475. So I was an all-star. I was supposed confused on selecting the series. And so Carter will do that here. Let me do that filtering data. BAS 475, Q3A, filtering data. You'll want to choose the name of a series. Thank you so much. I think it's like DJALI. It's the name of the goat in Hunchback of Notre Dame. And he's a jolly goat. The tip question, yeah, the tip question, you got it. Stat tool 1. Keep putting the questions in here. I'm going to take them out as we say them. Chapter 14, waiter tips. Waiter tips. Other ones. Let me see if I missed any. Cassandra said, randomly, a sample is chosen from a random. Okay, so let me put that. Stat tool 1, chapter 14. We'll do one more song right here. Sample chosen from randomly. Okay, that's got it. I think it's got everything. Any others? Good afternoon, Abigail. Great to see you here. Let's throw out some 100 points. Carbon monoxide, of course. Jackson. Jackson, do you have 2 accounts? Because you're on. I thought Jackson, you're a mod. Might be another Jackson, but we can make you mod too, Jackson. Carbon monoxide. There we go. Carbon monoxide and 3A and 3. There we go. Let's grab the 474 right here. Thank you for my 474 students being here. We have 3A and 3B. 3A and 3B. 3B. I don't know what those are yet. Okay, we've got some stuff. I do have 2 accounts. It changes. Well, if you need me to merge those points at the end, just let me know. If you want, I can make this one a mod, or I could leave it not a mod so you know which account I'm on. You're pretty easily. I was like, Jackson, I was like, you're one of my students. I know that name. I know that name. I second everything Carter has suggested. Abigail says, awesome. If more 475, I love it. Let's go here. We're going to get my Pearson loaded up. Oh, no. We're doing a, okay, let's go to this. Here we go. First question is the bus question. Let me take the time on it. MewBot, you handing out the points? You doing the points? Who's doing the points? Okay, so the first question is the canvas content. And there we go. So we're doing this one at 4:05. Here we go to the canvas content. Let's do it. Okay. Oh, no worries, Jackson, at all. Oh, MewBot's over here in the background. Move him to the other screen. There we go. And I'm good to go. Okay. Suppose the probability of a bus arriving on time is 54%. Now, immediately you want to take a note on this and write down the information you have and do something like the following. So if you get a test question like this, you want to take it down as a note and write probability on time equals to this. Now, what would you find right after this? Help me out. Let's do as many as we can do today. What would you do right after this? You have probability of on time. Now you want to probably find probability of what? Because the bus is either on time. You're like, oh, will this bus be on time or will this bus be what? So we can find the other one pretty quickly, known as like P and Q and complements. All those words we should know because P and Q are complements to each other. This is not really P and Q, but it's the same theoretical idea of a complement here. So if we have the probability of on time, what should we find immediately? Like that. Like start writing down the things you know. And then you can start to utilize those things. So I have the probability the bus is on time. And so exactly, Leo, right there, getting the probability of late pretty quickly. And great job, Leo. So you have the probability of late because the bus is either on time or the bus is late. And 1 minus the complement is the other one. Great job, Fleming, right there. More 100 points. Keep those answers coming. Keep the practice coming in. And so now what we want to do is we want to find out what is the probability the bus is on time for at least one stop. And this is where we have to learn to write the following sentence. There's only two things that could occur when 4 stops occur. Either bus is always late, or on time at least once. Now the problem specifies that we can use the multiplication rule. So independent stops. Now that will come into play later here, but when I write the bus is always going to be late, or the bus is on time at least once, what am I doing to these two events right here? What am I doing to these two events? If I say the bus is always late, or the bus is on time at least once. If I say the bus is always late, or the bus is on time at least once, what am I doing to these two events right here? If I say the bus is always late, or it's on time at least once, what am I doing to those two events? It's always late, or it's on time at least once. It's always late, or it's on time at least once. I'm adding them. So the word or right here means the addition rule. And these are mutually exclusive things. Think you're going to look at 4 bus stops, and the buses for them are either always late or at least one of the buses is on time. Does that make sense? The buses are either always late, like all 4 were late, or at least one was on time. It's like if I told you, I'm going to give you lottery tickets right now. So if I give you lottery tickets, tell me this. I'm going to give you 3 lottery tickets. So here's your scratch off lottery tickets with the scratch off things on them. Look like ghosts or something, weird looking ghost right there. So tell me, either all your lottery tickets could be losers or what? Either all the lottery tickets could be losers or what? Finish the sentence. Either all my lottery tickets will be losing lottery scratch off tickets or what? Now be careful because we have to do the complement. A lot of people like to say something that's not true. I don't want to say it, but either all my lottery tickets are losers. We're just learning how to write this sentence right here. That's going to be key to solving this problem. Or at least one is a winner. Exactly, Jackson. Like either all the tickets are going to be losers, or I'm going to win on at least one. So, or at least one. So make sure to do at least one, Fleming. Good work, Fleming, right there. Or at least one, because it could be 1's a winner, 2's a winner, or all 3's a winner. Because either all the lottery tickets will be a loser, or at least one will be a winner. Like if I were to win on the last lottery ticket, that'd be great. If I were to win on 2 of the lottery tickets, that'd be even better. Or it could be that 3 of the lottery tickets are winners. Or it could be that the first is a winner, the third is a winner, and the second's a loser. So there's many combinations, but the thing we would not want to see if we're buying lottery tickets is that all lottery tickets are losers. So either all my lottery tickets are losers, or at least one is a winner. And the same thing works for our bus problem. Either the bus will be late all the time, so we got 4 stops right here. Either the bus is late to the first, the second, the third, and the fourth, or it's on time at least once. So these are the only things that can occur. Since these are the only things that can occur, the probability here will equal to what? Because either it's always late or it's on time at least once to like all 4 of these stops. So what would this add up to? Because either it's always late to the first stop, the second stop, the third stop, the fourth stop, or it's on time to at least one. So the probability here would add up to what? Because this is the set of everything that could occur. We've listed everything that could occur. It's either always going to be late or on time at least once. So what would the probability add up to here? Because this has a probability and this has a probability, and we could add them. It adds up to 1. Exactly. So the easy one to find is going to be this down here, that it's always late. Great job, Leo and Jackson. The easy thing to find is that it's always going to be late, because the probability of it always being late is that it's late to the first, and it's late to the second, and it's late to the third, and it's late to the fourth. So this is the probability it's late to all 4 stops. As in, I gotta zoom out a tiny bit more, the probability of always being late is going to be 0.46 to the 4th power. And from here, it's just an algebra problem, because now we can take and go over here and solve the following way by just taking and subtracting this from both sides, which means over here it's going to be a minus for that. So now we have the probability that the bus is on time at least once is everything but it's always late. So 1 minus the probability of always late is the complement. It's on time at least once. And I like to do this solve like this. Do realize I did the multiplication rule here because the problem assumed independence. Since independence, not whatever, I don't know what I'm saying. Since independence was assumed, we could multiply. When we were adding events, we had to assume what? To add events with the or word, I had to assume that the two events were what, which they are, because they are complements, and complements have to be this, because they both can't occur, and that's what I'm trying to allude to. The green highlighting right there, by adding, I have assumed that the two events are what of each other. And do realize, I said the announcement last night that the formula sheet has hints, and the formula sheet does have hints for what we need to know. The formula sheet has notation on here. It has things that'll help with the problems. By adding together the two events, we did assume that the two events were what? Which they are. They're complements, so they have to be. Complements are always what? Hey, Priya, great to see you here. Got a lot to feel free to ask any questions. We got a lot lined up, but put some more. We probably got just enough time for a little bit more. Mutually exclusive, and that's also the word disjoint. So it's the same thing. Not dependent, though. Well, they might. It is true. It is true that complements are dependent, but the reason we can add them is because they're mutually exclusive. It is true that complements are dependent, because if one happens, the other can't. But the reason we can add them is because they're disjoint / mutually exclusive. When it comes to independent dependent, that goes to checking if we multiply events. There is some overlap between topics, though. And Leo, great job, Leo, pointing it out right there. There is little overlap where it gets confusing. Like, wait a minute. So disjoint events are dependent? It's like, yes, because if one happens, the other can't. It's like, so can we multiply them? So we actually can't multiply them. That's a good way to think about it. So we are supposed to add or multiply for this question. I'm confused on which one to do. You have to add and multiply. Good questions, Megan. About to study all the... Right here was the best way to start studying. 45 minutes study, 15-minute break. Use some of the videos here, Barrett. Good questions, Barrett. I would start going through videos and say, I'm going to focus on this video and take notes, and then use the video. Have your interpretations down. We might even take a moment today to do some interpretations. Sample statistics and population parameters. Yeah, let me put that on the list right here, Priya. You got it. It'll be a little bit. We should get to that. Sample statistics and population parameters. It is on the list. You're welcome, Barrett. And there's the link there, Barrett. Just real quick on that. So Barrett, when you're over here, try to be like, okay, I'm going to spend this next. Like if you go to a speedrun video, be like, okay, this video is 15 minutes. I'm going to stay here for this 15 minutes, and I'm going to be like taking notes and focus. And then I'm going to take a break for 10 minutes. I'm going to go, I don't know, make a sandwich or something. You can write on it during the test, Gary. Great to have you here, Gary. You can write on it during the test, but you can't have stuff written on a pre-test. Like before the test, you can't bring in stuff with the formula sheet. But during the test, you can write on it. And so, yeah, you can write on it during the test. But don't. You're not allowed notes for the test. But you can write on things. So like during. I hope that's very, very clear right there. Good questions. Let's head back to the main screen, start another problem. Thank you so much. We got a bunch of people here asking questions. We love it. Time for our next question of the day. More points in the chat. This is a tougher test. Don't let that discourage you. Let that be like, okay, I gotta do some prep right now. I got about a 20-30 hour countdown to the test. I sent out some advice to my students saying, know your interpretations. Be reviewing your Canvas content note cards. Has anyone been taking their Canvas content note cards? One of the things I tell my students to do is every Canvas content question you see, write down on a note card. Whether you see it during office hours, do both your tests of Canvas content, so take your Canvas content twice, and get every single question you can on a note card. I don't think it's bad if you even talk to friends and say, hey, you got some Canvas content note cards? What knowledge did you gain from it? It's all about that practice. So great job, Fleming, right there. Sports. It's all about sports today. The exam window is 7:30 to 11. Thank you there, Alea. Good questions. Some Philip DeFranco. Great YouTuber right there. About to do the waist size question next. So make sure if you have a question, put it in the chat. And thank you to everybody who's been asking all the questions and answering questions. You know what we like to do here? We like to practice. So the more questions we answer and the more questions we work on, the more people get practice. So if you hear me doing it, try to answer the questions with me. I'm going to try to direct your knowledge. There's some key things I want you to know about this question. Let's go do the waist size question. Here we go. Okay, so this is the waist size question. And this is the sampling distribution of the sample what? This is the sampling distribution of the sample what? So the waist size question is, how big is your waist? So this is the sampling distribution of the sample what? Where they are using an estimate of the population parameters to Priya's questions, which is the truth for all men, which they're kind of estimating. It's the mean. Megan, great job right there. We'll make Megan a mod. There we go, Megan. And so they are saying that they have the population parameters. Whenever you get a problem right here, the sampling distribution of the sample mean, great job, Jackson, right there. Whenever you get a problem, as Leo knows, shouts to Leo 100 points in advance. What do we always do whenever we get a problem? If you get a problem, you should immediately start taking down the what. If you get a problem, you should immediately start looking at the what right here. If you have a problem like this, crazy big problem, you're like, I need to immediately find the what in it. It's talking about we have estimates of the population from these men, and they have a mean waist size of this, and they have a standard deviation of this. So immediately we get these sort of problems. You're going to go here and say, I got a lot of information. I need to mark my what? Mean and standard deviation, which is going to be the notation, right? So tell me if you know what these values are. Now, if you have identified this problem as the sampling distribution of the sample mean, that means you need to go to your formula sheet. And on your formula sheet, you need to grab the following information. If you see sampling distribution of sample mean in a question, immediately start going to your formula sheet and looking at the formulas for it. So we have our information on the screen right here. So once again, be careful. I'm not going to eliminate it down. I want people to make errors if they're going to make them. What are the two numbers I've highlighted on the screen? Please note this is the sampling distribution of the sample mean because it's waist sizes and it's how large is your waist, which is a quantitative question. Pretty much. We'll put a green. Can you go a little further detail, Priya? Priya, good work. You're right, but go a little further detail. Go very specific. That is correct. I want to make sure people see it 100%. That is correct on the wording, Jackson. So where is that on the screen right now currently? People are giving correct answers. There's nothing wrong said yet. 100 points, nothing wrong. I want a very specific notation value mentioned. I'll highlight it here. What is the specific notation value you've been giving? In notation, you've been giving what? Priya's right, it's the mean. Jackson went more specific and said population mean. That is more specific and correct. So what specific value is that? Priya, that's why I paused. It's not P. It's not P. P is the true proportion. Priya, 100 points. It's not P, and that's why I want to make sure. It is mu. Because mu is for quantitative, and that's why I've done the blue right there. Red is for categorical. If we ask somebody like, do you prefer loafers? Or I don't know what it's, loafers versus something. I don't know. I'm thinking of shoes and stuff. But red would have to be a categorical question. That's when we deal with P, Q over N square root and P over there. So if the question was categorical, it would have a P, Q, and N. If the question is quantitative, which this one is, no worries, Priya. That's why I wanted to make sure, because if you say mean, you might have been looking here or something. But that's not what it is. The value we've been quoting has been this value. Does that make sense? Now we are going to use this to find the mean of the what. We are going to use this to find, and I'll do it here in black. We're going to use this to find the mean of the sampling distribution, because this value relates to the sampling distribution. Does that 2C? We'll take it. I think we have that. Let me put that on here, Adam. We might have that later coming up for 475. 2C here, I'll put that here. We probably have just enough time. We're going to try to get to as much as we can, but I've got that in the list, Adam. Q2C. If not, we will get to it later off the list. Okay, thank you, Adam. So this is the mean for the distribution of the sample mean. And here's the thing. The mean for the distribution of the sample mean is the mean. So for all of these questions, when it says, and don't look at this up here, that's a simulation. What is the theoretical mean going to be? 4D, I think we have that one listed. We did 4D yesterday. Check out yes, or was that 4C? We'll check it out 4D too. Tell me if we don't get to it. So for the theoretical mean, the mean for the distribution of the sample mean is going to be the mean. So tell me, what's the answer to every question when it says, what is the mean? Because it's asking for this value right here. So what is the answer to every single question going to be when it says, what is the theoretical mean for the distribution of the sample mean? It's going to be that for every single question. There's no sample size, no nothing. It's that. It's the same mean, because the mean is going to be the mean for the distribution of the sample mean. And that's what that formula over there states, is that the distribution of the sample mean, which is the y bar, will have a mean that is the mean. So this value right here is the mean for the distribution of the sample mean. That's what that says, the mean for the distribution of the sample mean. The sampling distribution has a mean, and we're doing the sampling distribution of the sample mean. A lot of, sometimes I even have a problem saying the words in the correct order. But also now it wants to know about the standard deviation. Teaching to the test moments. One of the biggest errors I see is when we ask people, what is the standard deviation for the distribution of the sample mean? Guess what people put for the answer? Guess what people put if we say, what is the mean for, what is the standard deviation? Take a wild guess, and I couldn't literally be teaching to the test more than ever with this question. What do you think people do when we say, what is the standard deviation? They put 3.97. They say, at 3.97, 3.97, 3.97. But that's not how it works. That's not how it works. Because this value will get water. What happens, and we'll point to the other one now. This value, the standard deviation right there, will get water for the sampling distribution. The sampling distribution standard deviation will get what? Smaller by a factor of square root of n. So all I'm going to do for all these questions is take 3.97 and divide by square root of n, whatever n is. So I'm just going to plug in exactly up here right there. So the standard deviation, it gets smaller, and that's part of the central limit theorem, that the which is a fundamental, teaching to the test, fundamental concept. I've been deciding to say that a little bit more often since I check over things. But the central limit theorem is fundamental to statistics. You'll probably hear me say that a lot on Wednesday. Whenever I mention the central limit theorem, I'll probably say it's a fundamental theorem in statistics. It's fundamental. Maybe you'll see something on the test. You're like, oh, it's fundamental. Boop. Anyways, going back here. Okay. So the standard deviation is not going to be the same right here. It's going to get smaller by a factor of square root of n. And so let's take 3.97 divided by square root of n. Put it right here. Don't even look at those values yet. Round to 2 digits. 5 square root 3.97. Good to see you here, Hunter. Be very careful. It's easy. I've got to do a correction for someone. I saw an email saying, Brian, small error. We will correct it. Don't worry. If you 1.26, I can do it in my head. Be very careful. Your values should be kind of close to the simulation. Simulations generally show what we would expect to see in reality. So these values are not going to match. But if one of your numbers is pretty far off, you've done a miscalculation. They should not match completely. But if your numbers are kind of close to them, that's a good sign. Like, I'm not going to freak out because that's 1.75 and that's 1.78. But if it was something like this, or not like that, but if it was something like that or that, I'd be like, I probably made an error. Your numbers are going to be kind of close to these. These are a simulation showing, a simulation to see if this is accurate, and because these are the theoretical values, like what the theorem says we should get, the central limit theorem says we should get. If they did more trials on the simulation, they would converge to the answers of the central limit theorem. Are the theoretical values close? The simulations are pretty close. At what point do they look similar? This is a nonsense question. The answer is 5. It's because it's basically unimodal and symmetric. Another teaching to the test moment. Let's say, would a sample size of 30 be large enough such that the distribution would be normal? Would a sample size of 30 in all instances be large enough such that the distribution of the sample mean will be normal? Would a sample size of 30 be large enough such that the distribution of the sample mean will always be normal? Is a sample size of 30 large enough that the distribution of the sample mean will be normal in all instances? Is a sample size of 30 large enough such that the distribution of the sample mean will be nearly normal? What are people's thoughts on that? Is no, that is correct. And why is it? Why no, Priya? That is correct. And read the slide. Good work. Good work. 100 points. Why no? That is correct. Why no? So the question was, is a sample size of 30 large enough such that the distribution of the sample mean will be nearly normal in all instances? And if you're responding to someone, you would say no, because in some instances, if it's very skewed, exactly, we'd need a larger sample. So you would need larger samples for higher skew, and that's why it's called large enough N. So the more skewed it is, the larger N needs to be. So the sample size needs to be larger for the larger amount of skew. 30 is not large enough in all instances. 50 is not large enough. So the more skewed it is, the larger N needs to be. And in this instance, it's basically kind of normal. This looks normal here. I don't like that. You kind of have to guess at that. But since it is nearly unimodal and nearly symmetric, it does not take a very large sample size, and we've done it. Another 100 points for the chat. Great work, everybody. Excellent job. Let's head back to the main screen. Keep those questions coming. Will you do activity 9 video? Yeah, we should do that. I guess we'll do that tomorrow, right? Woo! Tomorrow's going to be a busy day. Tomorrow's going to be... Whew. Great to see you, Kyle. Yeah, we should do that tomorrow because my class has it due next week. But Kyle, so good to see you here. And it's gonna be a busy week. It is. We got this little marathon before break. Little marathon. We'll filter some data. Talk a little bit about filtering stuff right here. Let me see. Q3A. Oh, did I not? Oh, I did. Oh, I didn't. Oh, yeah. So let's do this. Cool, let's do it. Keep those questions rolling in. We got a full docket of questions. Let's go do some filtering data. Okay. So yesterday I did some of this. My data did not need filtering, though. So this is what I ran yesterday right here. And no filtering was required, but your data requires filtering. When you go to the U.S. employment right here, U.S. employment has series in it. And so we've got here series ID. So we should be able to use the filter option. Does title have multiple levels? It doesn't say. It's a character. Oh, that's interesting. Let's pipe it through. Little Mario pipe. Filter series ID. There we go. Equals. And let's go to levels. U.S. employment. I want to take the first one there. No. There we go. Boop, boop. There we go. Just grabbing a random one right there. And let's see if we got it. We do have it. Ooh, employed as NA. Well, should run still. Be able to take, let's see if it works. Go ahead and take this right here. If you notice, a lot of code is copy paste. If you're watching this, copy paste, copy paste, copy paste. And employed, it's mad. STO definition are missing values. Okay, so it doesn't like our missing values, which is all right. I thought that'd be an issue. I wonder if the autoplot, I think I can fix this right here in a second. Let me see what the autoplot turns out. Okay, wow, that's a lot of missing values. Whoops, wrong button. That's a lot of missing values. The series only starts at like 1990. So I want to take and filter. I'm going to pipe it through a second filter. Filter. Let me double think. Hey, Brian, any chance you could help with 4D and 4E? Yeah, we're going to do some 4D and 4E coming up here soon. Yeah. I'm throwing this through a second filter right now, and I want to do is.na. This is going to cause an issue, don't worry. Is.na of employed. And then I'm going to, whoops. So that's the is missing, and that's the not missing. And then we'll throw another pipe. There we go. So I filtered out the values that are filter. Oh wait, well, it worked. Wait a minute. I should filter out the is and a's. Oh, somehow my brain knew what to do, but well, thank you, brain. Must have saw that somewhere at one point and thought of it. But now we've got that. It looks like we're good. We filtered those out. Now that we have this, let's remove the auto plot here, run it, and we're good. So sometimes things don't run instantaneously, and then you got to work with the data a little bit because all data is different. And yeah, I don't want to talk about this series too much here, but we got a lot going on with this. And so once again, the filter, some great stuff with dplyr right here. So Hunter, great work. Is this making sense, Hunter, how I went through here? I took the U.S. employment. I took a series ID. I just took only that series ID, so it's just a different series. It's like Walmart data, Target data, Best Buy data. So I took that data set right there. Then I said remove out the missingness because my data had a lot of missingness here. You can see at the start of my series, a whole bunch of missing values, especially when I viewed it. Viewing the series, at least over here, showed that there's all these missingness NAs right here. So we had all this missingness. So I went in and wrote the code to remove it. And once I saw that it was removed, I went in and did an STL decomp of it and got my data working here and got the components. So this pulls out the components of the STL decomp, and you could just view those visually if you want right here. That's the data frame with the trend, the series, the seasonal year, and you could put these back together in any way you like. Whether you're doing an additive or multiplicative decomp depends to you. Right now, we'd have to add them back together. But hopefully that helps out with kind of filtering data and looking at the STL decomp right here. But yeah, good stuff. Let's head back to the main screen. 4D and 3. Let me make sure I have those written down. Good stuff. 4D and 4E. BAS 475, 4D and 4. You're welcome, Carter. Okay. Good stuff. A little tiny bit of coffee. Tiny bit of coffee. I'm bringing the homework tonight, and I can't find the applet to do the homework. Can you send me the link to David M. Lane? David M. Lane should be in the chat right now. Thank you, Gabriel, for asking right there. Oh, happy wedding message from my uncle. Let me get... What does the mug say? Of course. It's the doctor mug today. The doctor. Trust me, I'm a doctor. You could trust him. He's a doctor. He's my favorite. Yoshi over there. That's your favorite too, Yoshi? Yoshi's the best. Introduced in Super Mario World, kind of Super Mario 4 for the SNES. Good game. Super Mario World. Such an amazing game. He has a doctorate. That's worth some 500 points. You should say on the other side, like, I have a doctorate. I like that. It's funny, it's my fiance's mug, and it's like one of my favorites. I just think it's so cute. I like cute things. Got it up. It's the waitress question today. Waitress. I'm sorry, everybody. It's a big week. And thank you, everyone. I've been trying to catch up on emails and Discord messages. Thank you so much, everybody who's been, like, please message me. Please let me know if there's an issue. Please tell me if you have to take tests early. Please tell me. I will respond as quickly and efficiently as possible, and then I will sleep. Back over to the main screen. Oh, let's do this. Time for the waitress question today. Here we go. So this is the waitress question today, and we have an individual who knows the distribution of their tips. Now, whenever you get a question, hint, hint, hint. Whenever you get a question, what's the first thing you do if you get a question like this? You get a question like this, first thing you're going to do is what? And I need your help for this because we're doing test practice. You can hear me say the answers, but this is test practice. A lot of people don't look at chapter 13 and 14 or get them confused because they're sampling distribution. Jackson, 100 points notation. So I'm going to mark the notation for you because I think a lot of people would find the numbers, but then I want you to tell me what these values are as I mark them here in yellow and mark them here in green and mark this here in orange. I think the orange is the easy one, but help me out find all the notation on this screen. The question they're asking is, how much is my tip? I'd say, what question? So they're asking, how much is my tip? And they're trying to find what they would expect for their average tip on 50 parties. So they're saying, what would I expect on an average weekend where I have 50 parties? Like, what would I expect to get on average? Their average tip on 50 parties is what they're considering. Ooh, kind of, Jackson. Kind of. You're on the right track. I think I know what you're getting at. I think you're right. You might just be the limited characters on YouTube. Jackson, 100 points. Specifically, and you're on the right track. No, I think you'd get it. I think you get it. Don't worry. We're like super doing our knowledge right here, Jackson. Jackson, I'm throwing you 500 points. Don't worry. This is what we do. Like, I want to show you. Notice the last question, someone got it wrong because I was saying kind of right, because I want to make sure we're 100% right and we see it. And so, Jackson, I think you see it. I think you're telling me it's this, right? And then are you implying that that will have us then find mu y bar? So mu y bar is one thing. It's the mean for the distribution of the sample mean. We won't actually multiply. A lot of people sometimes think you multiply those values. That's a phrase. The mean for the distribution of the sample mean. It's the expected value of the sample mean. It's a phrase. It's not a equation right there. So it's just mu. So the mean for the distribution of the sample mean is the mean. So we already have found this value right here. That value is 5.1. No. Oh my gosh. Whoops. Ignore that. There's the mean up there. I looked to the wrong value. See, I didn't do that on purpose. That happens. I was like, that's a smaller mean than usual for this question. So now the other value, Jackson, is what? There's two more values here. Don't worry. Good practice. What are the two other values on the screen for this question? We need to be able to identify these formulas and know what we have. So very specifically, what is the other value? Don't worry. It's just good practice. I think you'll get it. Or Madison or anyone else, let me know what the other value is. Fleming, you're on the right track. Fleming is correct. This is... Well, yes, it is standard deviation, but specifically what? Because there's a lot of standard deviation on the screen right now. So that value it gives you is what? It is standard deviation. That is accurate. Very specifically, it is what? The green value is very specifically what? And Fleming is correct. It's the actual for the population. It's population standard deviation. That weird is sigma. I'll take that, Jackson, for 100 points. That weird O Greek character, it's sigma. That is correct. It's the weird O Greek character. Yes, sigma. Remember sigma, standard deviation. Good way to remember it right there. Don't worry, you don't have to memorize what it's called. As long as you know what it is in the formula sheet, you're good. And so what do we need to then do right here? We already know the mean of the distribution is going to be 9.40. We already know that. So now all we need to do is solve for the what? And one, it's again, teaching to the test moments. We know the mean. The standard deviation is always for the sampling distribution, not for the original data. But the sampling distribution has a new standard deviation that is what? The original standard deviation divided by square root of 50. Well, in this instance, square root of n always, but we take the original standard deviation and divide over the square root of n exactly. So this is the central limit theorem again, that the distribution gets smaller and tighter. Central limit theorem is a fundamental thing for statistics, fundamental theorem. So 50 square root, fundamental theorem being used right here. Point. And now, great job, Fleming. Good practice along with me right here. Double check on the calculator. I appreciate the double check and good practice. Great work. And I'm pulling up the David M. Lane right now. You won't use this on the test. We could draw this out, but on the homework, you will pull this up right here. Once again, every time I do this, just realize, I think it was 9.40, right? And then you could just take, it's not the value. Make sure to put in the actual one, the new one. I could draw this out on a sheet of paper, and since we're more limited on time day, or we're trying to get through as much as we can, all you do is go up the standard deviations and down the standard deviations, and now we have the curves that we need with the mean and the standard deviation. Let me double check and make sure we have the right mean. The mean is 9.4. Good stuff. So now it asks, they want to make $550 on 50 parties. So if you want to make $550 on 50 parties, how much would you have to make on average? Because we're doing the distribution of average tip. So you're saying, I want to make $550. So what would you do to this to figure out, well, how much do I need to make on average on 50 parties? So what would you do? Or what's the answer? If you say the answer, I'll tell you how it's found. I want to make $550 on 50 parties. I would have to average this tip. So you want $550 from 50 parties. Now, what would your average tip need to be to meet this goal? What would you need to do to solve this? Just to find out the average tip that you would need. How do we find out on average I need to make this tip? And what would we do? Well, we want to make 550, right? And we have 50 tables. Great job, Jackson, right there. So we would need to average. Great job, Cameron. Great job. More button presses. Yep. Divide by 50. Divide by how many tables there are. And so if you notice right here, $11 is over here, which is going to be like 1.8% probability. We need to go to the first curve, and we need to go above $11, which is what we calculated, about 1.8 probability. It's 1.3. Yep. Adam's like, I remember this one. This is a classic question. One of the tougher questions all semester. So that's the probability right there. Once again, I went above the average tip needed. Now it says the best 1% of weekends. This is where we have to use the second button. So make sure to click the second button and put in the best 1% of weekends. Now this is my what tip on the best 1% of weekends. Because think of what the distribution is, the distribution of the sample mean. So this is my what tip on the best 1% of weekends. So put that word, and then I'll show you how to use it. This is my what tip on the best 1% of weekends. That's not how much I made all weekend. That was my average tip. So I'm going to multiply it by my 50 tables, and I made $553.90. That was my average tip. So you're finding the average tip and multiplying it by 50 to figure out what you would get on your best weekends. And that's a tougher question. It's 2 blanks with a lot of background work. So make sure to follow through here, solve for the mean of the distribution, solve for the standard deviation, plug in the numbers, and then use the numbers to solve for the best average tip on the best 1% of weekends. Also solve for the probability of obtaining the goal, and the goal is relative to the problem. Check out those steps. Let's head back here to the main screen. Good, tough question right there. Good one right there. We've got sample is chosen randomly. We've got 2 more 201s, then we got a 475 coming up next. Human pregnancies. Carbon monoxide. Was there another waste one? There's 2 waste questions. Ah! We didn't do the other waste question yet. All right, cool. Theory question. Sample is chosen randomly. This one will be pretty quick, I think. Here we go. The sample is chosen randomly. Let's do it. A sample is chosen randomly from a population that is described as by a normal model. Now, when you hear something is described as a normal model, how large does n need to be? Now, once again, we're trying to do as many teaching to the test moments as we can do. If you hear that something is described as a normal model, how large would n need to be? If something is described as a normal model, how large would n need to be to do the central limit theorem? And we talk about the conditions, and if we meet all conditions, then the distribution of the sample will be normal. Great job, Jackson, right there. So does 30 work, Jackson? Does 30 work for everything? Like if I said I have a sample size of 30, would that work for the sampling distribution of the sample mean to be normal? Because that's why we check conditions, so that the sampling distribution of the sample mean can be normal. We don't check conditions to calculate the standard, the sample mean, the anything. The reason we check conditions is to make sure that this distribution, where's that distribution? This distribution right here, that parent distribution, when we do the sampling distributions will become more normal the larger n is. So the reason we check these conditions is not to calculate anything other than to know that the distribution will be normal. So the larger n is, the more normal it will be. You can see it right here. As n gets larger, the distribution becomes more normal. And after a certain point, it's basically nearly normal. Now, do remember the third condition is called large enough n, but the central limit theorem relates to it being nearly normal. Kind of a global idea right there. But the condition is, for this chapter, called large enough n. And they're saying right here that it's normal, so it's going to be normal when we talk about the distribution. What's the sampling distribution model for the sample mean? Describe the shape, center, and spread. Okay, cool. Normal, well, that's not helping. With a center of what? What is the center of the curve? Well, I think we can eliminate, I I think we can get this super quick. What's the center of the curve? Let's go over here to one of our notes and just take this right here, do a new sheet. What's the center of the curve? So it's normal with a center that's what? What is the center of the curve? Now, it is mu y bar. That is the mean for the distribution of the sample mean, but the mean is also what? The mean for the distribution of the sample mean is... It's simply the mean. So if you go over here to the question, it's this one. And the standard deviation is the original standard deviation divided by the square root of n. Don't forget to divide by the square root of n. If a larger sample size is chosen, what will be the effects on it? Well, checking the equation, what happens to it? What changes and what decreases or increases? What changes about the distribution if n gets larger? If n gets larger, what happens to it? Don't even look at the answers. We can figure it out theoretically from this. If n gets larger, so if sample size is larger, what will happen to the distribution? Who knows? Ideas about that. So we have don't worry about the answers below. Just think, well, this will happen. Because the mean is the mean, and the standard deviation is the original standard deviation divided by the square root of n, right over here. So the new standard deviation for the distribution of the sample mean, that's not an equation, it's a phrase. The standard deviation for the distribution of the sample mean is equal to the original standard deviation over the square root of n. So if n gets larger, it's in the denominator. See if anyone knows. It's one of the two things of the central limit theorem. The curve gets tighter, which this doesn't show. We showed it theoretically a moment ago. But also, it'll have a smaller standard deviation. The standard deviation will be smaller and the center will remain the same because there's nothing changing the center right here. The standard deviation is what gets smaller. And that should do it. Oh, wait, what? Nope. Check answer. There we go. Submit the quiz. Good work. 100 points. Let's go back here to the main screen. Here we go. Okay, I think we have some 475. We have carbon monoxide. So join in. Carbon monoxide time. Almost done the whole quiz. Carbon monoxide question. Here we go with carbon monoxide. Let's do it. Okay, the carbon monoxide question is about a fleet of cars. Number one thing to do whenever you get a problem, especially for later in the class, is always mark the notation. So here's our notation that we have access to right now. Gotta take the best screenshots ever. Good, that's a good screenshot. And now we're gonna take our notation sheet right here. I'm gonna pause, I need help for this. Does anyone see? I'm gonna highlight the values and I want you to tell me what these values are. We've been practicing this a lot today because if you get a problem like this, immediately go to your notation sheet. If you see something like this, if you see something like this, and if you see this, tell me what those values are. So I'm taking a good pause right here. Oh, that's too big of a pause, Mewtwo. Mewbot wanted to join in there. What are any of these values? I'm just going to relax. We'll see who's here. Correct, Jackson. 100 points, Jackson. That's the value of Mew. Keep going. Jackson, good work. You're getting practice for the test. Now, if it said, what is the standard deviation for the distribution of the sample mean? And the reason, Jackson, excellent work, Jackson. Great practice. So the reason, great job, Megan, right there. The reason that this is the second one is because we're asking how much CO2 does a car produce? It's not does a car produce CO2, which would be categorical proportion questions. We're asking how much CO2 does a car produce? This is quantitative. This is categorical. Sometimes I figure maybe someone is only watching like this part, which is fine, I'm just like, I need to make sure to mark as much as I can and explain the difference between the top one, which is categorical questions like, do you like Taco Bell? And the bottom, which is quantitative, which is how much money do you spend at Taco Bell? So we could do those sampling distributions when we sample the population. So with these right here, we can find the mean and the standard deviation. Well, the mean is the mean. That's the easy one. It's 2.504. The standard deviation is the original standard deviation of the square root of n. And so there we are. Original standard deviation of the square root of n. So go point. There it is right there. And we're going to bring up some David M. Lane. Once again, we could draw this ourselves because all I'm going to do is have David M. Lane plot the center of the curve for me. Just expedience of doing the problem. Is it 2.504? 2.504. Use your new standard deviation. Don't forget that. I've made that mistake before. Check to see if it's 2.5. It is. There we go. Here's our curves. Once again, you could draw this by drawing your normal curve and putting the center, which is the mean, then go up a standard deviation, up and up and down and down and down. This is the units by which you go up and down each time. And so now let's look at what the question asks. Because once again, if we know how to draw the curve, we can get a lot done. Well, it's a normal curve, and we know what the mean is. The mean is 2.504, and the standard deviation is what we have. 3 decimal places. And what is the what is the area between 2.6 and 2.7? Oh, see, we should guess it. 2.6 is right about here. It's between a 1.28, a z-score of 1, and so it's got to be somewhere between 5 and 10%. It's going to be like 7%. 7%. Because that covers most of the curve. 7%, I say. 8.7%. So close-ish, close. Should guess a little bit more. And we go back. So all good. All's good to take a guess, see where you're at. And that needs to be removed. Tell me if you make a rounding error like that. We'd correct it. Now it wants the top 5%. Now, interestingly enough, I can actually guess this one. Watch me get it wrong. Oh, no, I've got it. Because the top 5%, the one you need to go over to the second button, the top 5% is going to be right about here. It's a z-score of 1.645. The z-scores are always the same. So it's going to be at 2.6. Luckily, this has like a big... just rounding to 1 decimal makes it a lot easier to get. And so if I do the top 5% on this curve, before I hit enter, I'm going to show you where it's going to be at. I'm going to hit enter once I put it right about, 1.645. It's going to be right about there. A little bit over right there. And so I know the z-score of that in my head because I've done this a lot. The z-score of the top 5% is 1.645. And there it is right there, 1.6449 if you want to be exact. But that value is always constant as a z-score. So since I know where the z-score is at, because I've done this a lot, when I see the top 5%, I say to myself, well, it's right here on the curve, and I can kind of tell that that would round to 2.6. Now, you're not meant to know it that in depth. You're meant to maybe look at this, and we could ask you something like, what is the z-score for something that is at 2.7? That is a possible test question. Now, if you have drawn this visual, which you can draw by just drawing the curve and doing it, you could take the observation of 2.7, subtract from the mean of 2.504, divide by the standard deviation, and you would get 2.733. And that's where 2.7 would be at as a z-score. So the z-score is how many standard deviations you are above. And that formula I just did is right here. The observed sample mean minus the mean of the distribution, excuse me, over to the standard deviation. So once again, I took the sample mean of 2.7, subtracted the mean over there of 2.504, and divided by the standard deviation to turn it into a z-score. Just a hypothetical way we could do these sorts of problems on the test, rather than you solving for a probability, which you really can't solve for without the applet. Once again, everything on the test could be done theoretically by drawing it out. But usually the test question is a lot simpler, asking things like, what is the standard deviation of the distribution? A lot of people... for 1,000 points, what do you think a lot of people forget to do when we ask what is the standard deviation for the distribution of the sample mean? What do you think? I'm pausing here before we get to the next question, a little 475 after this. What do you think a lot of people forget to do when we say what is the standard deviation for the distribution of the sample mean? When we are asking for this value right here, that value, what do you think a lot of people forget to do? What do you think a lot of people forget to do when we're asking about this value right here? We say the standard deviation for the distribution of the sample mean. What do you think a lot of people forget to do? And I'll give you the wrong answer. I get so much. They usually say 0.6. And I say, no. And they're like, what? Like, that's not it. It's not 0.6. Divide by the square root of n. Exactly, because this is the standard deviation for the distribution of the sample mean. The mean is the same value. The mean is just the mean. The mean is just the mean. That's just tomato, tomato. It's the same thing. But a lot of people just forget to do divide by the square root of n because like, well, that's the standard deviation, right? Well, that's the original population standard deviation. So that's for like all cars. But we want to know for a sample mean what would be expected as a standard deviation. Not really expected standard deviation, but the variation in the sample mean that we would be drawing from. So there's a lot of times this forgetting to divide by square root of n, which a lot of people don't do. I just see that very commonly, and then I've been asked, like, wait, why'd I miss this? And I'm like, I'll tell you later, but I don't know. Just saying. But that's probably the biggest error I see is because you just see standard deviation. You're like, oh, it's standard deviation right there. But it's the standard deviation for the distribution of the sample mean is the original standard deviation divided by the square root of n. It gets smaller, central limit theorem. Heading back here to the main screen, more 201 coming up in a moment. Don't leave if you're 201. Wrong button. Between scenes, I like readjust and I'm like, I just get ready. I'm like, okay, I got this. So I usually just like sit up straight in my chair. Oh, that's how I get my exercise. Just do some lifts right here. I don't know. Sit in a chair for a bit. You gotta do a little, gotta move around a bit. I am ADD. I am just ball of energy, hyperactive. I never was diagnosed ADHD. Anyone else ADD in the chat? It's okay if you want to say or not say. But I was definitely diagnosed ADD as a child. My parents said, Brian, you're ADD. And I said, huh, what? And they said, case in point. I said, it's okay. It's okay. Let's take a look right here. Little 3A. Do similar but different work as per usual. 3A and 3B. Let's go do a timestamp. Timestamp 5740. Here we go. 3A and 3B for 475. Let's do it. We got some awesome passengers right here. This is Australian flight data. The total number of passengers in millions from Australia air carriers from the period of 1970 to 2011. And that's just a little data set. Use the ARIMA model to find an appropriate model. Model was selected. Check the residuals. Look for white noise. Do they look like white noise? Plot forecast for the next 10 periods. Okay. So we're gonna do similar but different work. Once again, if you want to look at a series, usually you can just auto plot it. And there's the series. If you're in 475 right now, you should see it. This definitely has a what. Definitely has a what. Like, if you see this, you'd be like, wow, that has a this. I don't know if anyone's 475 here. But if you're 201, you might think this looks like a linear model. So you're in 201, you say, ooh, it looks like a linear model. This is not good. So yeah, trend hunter, exactly. That's got a trend hunter, 100 points. Can we do the GG time series residuals on this? It's in fees. It doesn't like it. I think we got to pipe a model through that. Oh, good. Here we go. Yeah, that's trended data. That is the epitome of a trended data set. There's so many similar codes. That's why I use the book so often, because there's like GG time series residuals, GG TS display. The ACF right here, that pattern in the ACF is one of the most notable patterns to know immediately for trended data. So yeah, differencing is going to be needed. Like, yeah, this is not right now. This is not a clean residual plot. This actually goes to 201 because in 201 we do have residual plots. So if you're 201 and you're hearing this relates to chapter 7 and 8 a little bit because that's like a linear model right here, and that's not a white noise pattern yet. I'm going to change the series a little bit. What do we have? What? Let's go OS retail. We were talking about filtering earlier. We're gonna have to filter this down a little bit. We'll go to series ID, filter by series ID equals boop. Spaces we don't like. cool. And it's selecting turnover. So it's taking the, yeah, well, this is good. Look at that. That's got a trend also. We'll put turnover in here. That's got a trend. So, yeah, that's good. That's similar but different. We like similar but different. For question on 27201, I can't get as far as calculating the standard deviation of y-hand z-score. How do you find that? The David M. Lane. Good question. Which question are you working on, Ezra? We can go back and check that out. We might have done it today. I can show you the questions we've done, but let me know which one you're working on. The David M. Lane will allow us to calculate the find the probabilities. And you don't have to find the z-score actually, but no, let me know which one you're working on. We can check that out, or I can tell you which part of the video we did it today. Question one, tell me what question one says. Is it the waiter waitress? We did that, but let me know what it is, and then I'll tell you where it's at in this video, and you can watch me solve it, and let me know if you have questions. So thank you, Ezra. Where's my code? Well, I'll just rerun it through it. Which GG is it? What's the most important thing to know for the test? The central limit theorem is a fundamental part of statistics. Wow, this data is even more trended. Is this the one I did yesterday? This is some trended data right here. And you can definitely see differences in the monthly patterns down here with the GG, what is that? The GG season plot. So it's doing a GG season plot right here. Or no, that's by year though. Yeah, so, well, these are the months. So there's a little peak here in March. But you can see the yearly trend upward as years get later. It's the waiter waitress problem. That is in today's video. If you look over here, we did the waiter waitress problem at the 34-minute mark. So you should see about a 7-8 minute segment of the waiter waitress problem after I filtered the data. So if you see these right here, take a look at this screen. That's where we did the waiter waitress right here. And we're currently, so it's about 30 minutes back. So yeah, let me know. And we go back and check it out here in a little bit. You're welcome, Ezra. Thank you for asking. Good stuff. I'm glad you can always rewind these videos live. A lot of people don't know that while you're watching live, you can just rewind video. Then you can click watch live. This is trended data once again because the ACF shows this pattern that is very highly correlated at all lag points. You can also see a linear pattern. It's indicative of a trended data, that there's a trend in the data. Little change in slope right here, or yeah, change in slope, change back, change in slope, change back. Mostly somewhat positive linear relationship. Use the ARIMA to figure out the appropriate. Check the residuals. Look for a white noise pattern. I'm gonna cheat. I love cheating. What is the ARIMA stepwise auto? I always forget the ARIMA stepwise auto because it's so beautiful. It's so amazing. Where is my code for it? It's gonna be the model code. Here it is. Yeah, it's so easy. Yeah, I can't remember it. Okay. The book is your best friend. It's my best friend too. What are we predicting? We're predicting turnover. So let's put our Y variable in here. Oh, let's take a look at all these models. Okay. And should run these. These are going to store into models. Let's say fits. Oh, no. There we go. So Hunter or everyone who's 475 is here. Does it? Wow. Didn't think it'd run that fast. What would I probably want to look at for these models? What do I want to look at for these models? That's interesting. What would I want to look at? This is chapter 9, I believe. Chapter 9. I'll show you the page I'm at. I'll put it in the chat. I went straight to here, Hunter. Here's where I'm at. The AICs, exactly. The AICs. Great job, Abigail and Hunter. The AICs. I went straight to this page on the ARIMAs. And we're picking the proper order, which is a lot of what we're going to talk about today. So trying to see if we get a proper order, and then we need to probably select one of the models right here. So the we should be able to view it. Probably would just take a look. He does pivot longer on it, all this good stuff. But we can probably just view the table of fits. Let's go view it. There it is right here. That's messy. Ooh. Well, let's look at the fourth fit. There's the third fit, because the first thing's that. Here's the stepwise. So in comparison, and then we need to know how to read this. This actually goes back to last class. Great job, Adam and Abigail. 100 points, everyone right here. Could you tell me what differencing was used? could you tell me, and I think that's the question, what model was selected? Check the residuals, look for white noise. Could you tell me what differencing was used right here? Can you read this output? The ARIMA model stands for autoregressive, and that's the first value right here. Let me highlight it. That's going to make it easier to understand. So what I want to point to and what we should be learning about this is how to read this output and know what it's communicating to us. So here's the output we have. And okay. Does this make more sense to this output now? Especially if I start color coding in here. Who feels like they're understanding this output right here and can see what's going on with this output? Tell me your questions. Let me know. This is for 475 to make sense of what's going on with this. This is a seasonal ARIMA, so it has two components right here. And the two components it has is it's trying to understand both the seasonal and the non-seasonal pattern. We have here the amount of differencing that's been done. The differencing was done to the non-seasonal components. We have non-seasonal differencing. That was to detrend the data. And then we see that the other components of it, the stepwise, which was the selection, I think I put stepwise equals false, so it's a full search grid on it. It found the model of a autoregressive 1, moving average 2 with differencing of non-seasonal of 1. The seasonal component had an autoregressive 2 pattern. Who's following me with this? 475, what's your questions? What's your thoughts on this? Do you understand how to read this now? I'm hoping that color coding can help. Please put questions in the chat if you have it. I do realize there's a lot on this screen, but we should know what every one of those values mean and how to interpret it to somebody to say, well, this is trying to make model estimates. It's trying to figure out how many autoregressive coefficients do we need. Makes a little more sense. But when you think about it, it's like a regression model. Like you have here, because if we look at the full model, the model is going to have, I think we could run a report on it. Let me try doing a report on it. You don't need to look at them. Let me know your questions, Abigail. Any questions you have, because we'll be talking about this a lot today. If we go to our fits right here, and we should be able to go to select. Okay, let's go to select and select that. Okay, cool. That's selected. I see. It works. Then we go right here. Go with Fern. And then we're going to just pipe it through a report. Oh my gosh. Oh, whoa. Stop. I hit the wrong button. Cool. So when you look at this model right here, this is the stepwise. So in this model right here, you have a moving average 1, moving average 2. You have a seasonal autoregressive 1, seasonal autoregressive 2. And take a look right here. The seasonal autoregressive has 2 coefficients. Then you could report on that. We're going to tell the graders to be, because there's a lot of ways to go on this. And I'm doing a different series. That it looks like that's a non-seasonal atom. That if it only has that, that's a non-seasonal with 2 differencing done twice and an moving average 1. So I almost misspoke because I'm on an AR2 right here. But does everyone see the seasonal autoregressive right here is this? Does that make sense? These are the seasonal autoregressive coefficients. These are the estimates. These are the standard errors. So these are what we estimate the coefficients to be, and this is our uncertainty in the coefficients. This one has a... Oh, it doesn't have. I moved the decimal wrong. It's like these are your betas right here. Does everyone understand if I say like these are your betas for regression? So these are the betas, which are your estimates, like your slope and your intercept. Not quite the same. And then you have standard errors, which are uncertainties in the estimates. So we need 2 autoregressives, first order autoregressive and second order autoregressive on the seasonal component. That's why it's over here in the seasonal component. Then we have a moving average of 2 right here. The moving average of 2 is going to be right here. Why is there nothing for this? What does that mean, and why is there nothing for this? There should be nothing for it, because what did it do? What does it mean? So think about what it did and what it means. So what did that do and what does it mean? because we're looking at this right here. What did that do and what does it mean? Use the color coding to be like, well, that doesn't give you coefficients. That means the data has been whatted. So what does that do and what does it mean? We're talking about that green value right there that I've highlighted. There's not going to be a coefficient for that. What does that do and what does it mean? Yours might have difference. Well, this one has differencing of 0 on the seasonal component. With drift, then it's doing the drift estimate right there. The point between the first and the last is going to get a linear drift estimate right there. So it's going to use a drift component. So in my model, the differencing is 1. So that just means the data has been differenced. When you difference the data, like if you take a vector right here, like here we can make a trended data set. So here's a vector. We'll call the vector x. And if you go here and go to diff, which diff doesn't work on, you have to use differencing on data with Tisbel format. But that is the difference data. The difference data is between 1 and 5, there's an increase of 4. Between 5 and 6, there's an increase of 1. Between 6 and 4, there's a decrease of -2. So what we're doing here is we're actually differencing this data. That doesn't make coefficient estimates. Does that make sense, Abigail? Like if I difference the data, it's kind of a what on the data set. So fill in the blank. Differencing is a kind of, I would say it's this of the data. It's a way to change or what the data. So we're not going to get estimates for coefficients of differencing because differencing is more of a what of the data because the data is going to look completely different now. Differencing is not going to create estimates of coefficients. It's more of a what of your original data frame. A transformation of sorts, exactly. If you notice right here, the units go from about 5 to 50. Should be able to get our GG time series residuals. Nice. Remember how the units went from 5 to 50 or so right here? Now the units, and this is how much we miss by, but the units are very different because these are in difference units. Also, the series right here looks pretty good. If there is any problem, which I could try to fix this, if there's any problem with this data right now, what would the problem with this data be? If there's any problem with this, I mean, I don't love that, but it's not the worst. I've seen worse. But if there's any, I think it's maybe two issues. And yeah, differencing is kind of a changing your y so that it's not values of original y. You're looking at the differenced values of y. Whether you difference it once or twice will be controlled by this value right here. If it's 2, it'll be difference twice. If it's over here, it's seasonal differencing. And as the book says, it doesn't matter which one you do first. It doesn't matter. You can seasonal difference or difference your data. Seasonal differencing would be taking the difference between each season and using those estimates as the values. Where differencing is differencing between just the values we saw previously right here, where we took our original series 1, 5, 6, and then we took the difference. 1 and 5 has an increase of 4, 5 and 6 has an increase of 1, 6 and 4 has a decrease of 2, and that's what difference data is, which will detrend the data. Very important stuff for the final. How are we doing on this? Has this helped people out? Were you able to get the code? How's it looking? Once again, the most important things here a lot of times are the theory. Like, why are we doing this? Why would we detrend data? Is this a good white noise pattern? For the most part, I'd say that this is white noise. I have concerns right now, a little bit of heteroscedasticity here at the end. That's plot thickening into a 1. The ACF comes out mostly clean, but, and can we do partially equal true? Is that not an argument right here? I thought it was. PACF, I want to see the PACF. Type equals, I think it's type equals, and you can do type equals partial. Quietly. Why do you put things in here? Oh, it doesn't like it. I thought. I might actually look at it real quick. He calls something else. I remember Kayla and I were looking at this. He calls GGTS display. I hate that. We had to recode this. How can you tell if it's white noise in this case? We could probably run a test on it for white noise. Let's go look at white noise tests. Let's run that real quick. Let's run it through a white noise test. That's going to be a really good definitive. Let's see here. Where is it? What is the name of the test again? A lot of these tests are overly sensitive, especially for larger data sets. So you can get tests that come back statistically significant where you're like, what should a white noise pattern mostly look like? Like I'm going to run the test here in a moment. But what should a white noise pattern mostly look like? It should look mostly what? What should a white noise pattern mostly look like? Like if this is white noise, it's going to look mostly what? It should be centered around 0 because it shouldn't be off 0 because that's not random. A white noise pattern is going to be centered around 0, look random, not have strong heteroscedasticity. Mubot loves some randomness in the chat. It's going to look very random. And let's see right here, because where is it? Let's go. There's a test for stationarity of data. I'll run it on this to see if this is mostly stationary. Let me go grab that. We were doing it during the exponential smoothing, weren't we? There's certain... Where is it? We had it last class. Let me write stationary over here. And then we're going to do one more tool on. Models with stationarity. Where is it? Stationarity and differencing. Here it is. Here it is. A little chill music while we do this. Get the code. Let's go back to the slide. Found it. All right. If the data is stationary right here, we would not need a unit root on it. So this is not the original data anymore. After one order of differencing, is the data stationary? Well, first, we could take the original data and just see if it's stationary. Let's take the original data. So if you want to know if your data is stationary to start, which I can tell you, that's not stationary. That is not stationary. We can pipe it through right here. Turnover. And this comes back saying, yeah, there's a problem. So that's going to come back right there and say, yep, you got a problem. So now we're going to take it and go through here and take a look to see what the unit root of it. Oop, because we don't have the right thing. Turnover. There we go. And oh, that's still the unit. I thought we were getting the here it is. And it says we should do one differencing. So this converges. How do we get to the next 10 periods? We need to do a forecast. We're going to come back to that, especially later. We need to do a forecast on this and put the horizon to 10. So make sure to do a forecast with your model, horizon 10. Does that make sense, Hunter? So you want to do a forecast. Take your model. Do a little quick right here. So we got our fit. We've selected it. A little fun with 475 right here. A little 201 next. Forecast. Horizon equals 10. There we go. And let me do this. Forecast. Forecast not found. Let's save into it instead. And now let's go to auto plot. This is where I got to practice. No. We take the data. I always get this code wrong, and I had it down. I've had this code down. We take the data, and we pipe it through, and we auto-plot the forecast on it. That's not right. That's not right. That didn't do it. I know this. I know this pattern. Because here's the problem. If you auto-plot the forecast, you only get the forecast. So if you run this right here, you just get the forecast. I've done that a billion times. But what you want to do is you have to pipe the data through it. That's not going to be right. Oh, no. I think this is it. It's so weird. No, it's not it. Unless... No, it's not it. I will throw 500 points. Because I always have had this problem where I'm just auto-plotting the forecast. And I've done it in class. I've done it here. And then the code is, you have to, is it auto layer? Is it auto plot? Okay, let me try this. Let's go here to this, pipe through here to auto plot. Boom. And that's going to just show the series. Well, really? Whoa. Oh. We don't want that. That's crazy. I was like, what happened? Okay. Auto plot. There's the series. And then plus auto layer. There we go. There we go. That's got it. You have to auto layer the forecast on it for the next 10 periods. Does that make sense? It's a plus auto layer. Learning the FPP3 format. Once again, the book is always so. Sans book right there. Good practice. Just to try to make sure you can remember the codes. It's always good to use the book as a resource to go to his codes, to look at his codes, to practice the codes. But even I try to remember, like, okay, I got to remember that code off the top of my head. How do I do it? How do I get the series plotted? And once we're here, we can use our general ggplot options of plotting this to take the series. We can just call it graphic P. And if we have graphic P, we can just go here and go plus GG title, and not GG text, want GG title, and give it my title. And then we can do nice and easy things like library GG easy, and go to easy center title. And there we go. Good stuff like that. If you have questions, let me know. Try to make your graphics look as nice and neat as possible. That's the goal, is to practice. And there's a lot of easy things we can do to make our graphics look even better. But with that, do we have enough time for any more 201? We might have lost all the 201ers. Sample statistics and population parameters. This was a good end for 475 right here. Any other last questions? I'm going to check on our bunnies. Our bunnies was doing a little bit sick. But can we do some interpretation? Yeah, let's do interpretations. So here we go. Let's do those to end off office hours. So Leo, such a great question. Interpretations is a great way to end office hours. So let's head over here to do stat 201, test 2, interpretations. Okay, here we go. So when it comes to interpreting values, what 3 values do you need to be able to interpret for test 2? What 3 values do you need to be able to interpret for test 2? What 3 values? Same data. Trying to open a new data set. What 3 values? As Brian looks for... Oh, is this one new? We might finally have a different data set. We're using a different data set. Kind of, Leo. Good. So not quite x, y, and r squared. R squared is one of them. Good answers, Leo. 100 points. Not x, y, and r squared, but the slope, the intercept, and r squared. So the slope is b0. The intercept, oh my god, the slope is b1. The intercept is b0. And the r squared is r squared. So let's go take a look at those right here, and let's make a model. Now, if we're doing a regression, we need 2 quantitative variables. So slope and intercept, exactly. And so I'm going to make it so we only have quantitative variables here. And let's look at predicting. We're going to do maybe an easier one. Let's look at how dateable people think people are. That's weird units. People's weight. And let's have that predict how many drinks they drink a week. How many alcohol drinks they drink a week. Okay, so this has problems, but let's look at it. Okay, we got something. So we got people's weights and their alcoholic drinks. And we'll put drinks week right here. I think we still have our sheets up from the review. Where we did the review. Did I not write down? Here we are. So this is our review. We're reviewed on test night, and we're going to use a similar thing right here. Let's take this output right here, delete it, and let's input the new output over here where we have our model, and I'm going to delete down decimals and make it so we can interpret it. And here is the model. So there it is right there. Let's go grab the linear fit. And there's the linear fit of the model, which is the parameter estimates. And what do we have right here? We have the intercept value, and then we have the slope right there. The intercept, we'll delete those off. And I think we are good to go. Got a lot of craziness right there. Okay. So, Leo, can you interpret the intercept for me? The intercept is when x is equal to 0, we expect y to equal b0. When x is equal to 0, we expect y to equal b0. When x is equal to 0, we expect y to equal b0. When x is equal to 0, we expect y to equal b0. So use the numbers on the screen. And I can read the answers, but if you're here practicing, if you're watching this later, try to do it. I'm going to say the answer. Write it down. I'm not going to write it down. I'm just going to use the blank interpretations. When weight is equal to 0, we expect drink consumed a week to be exactly. And so does that make sense, Leo? Does what you just said there make any sense? You said when weight is equal to 0, we expect drinks consumed on average to be equal to that. So wait, that does make sense? No, it doesn't. Negative, right? You can't have negative drinks. And you're welcome, Hunter. Excellent work right there. You can't have negative drinks drank and somebody can't weigh 0, right? So you'd say this is illogical because you can't have negative drinks and someone can't weigh 0 pounds. So when x is equal to 0, we'll highlight what x is here. So x is weight. So when x is equal to 0, we expect y, which is drinks a week, to equal b0, which is the value. So I'm color coding what you would input here. When somebody's weight is equal to 0, we expect drinks a week to be equal to negative 4.06 on average. This is not logical because you can't weigh 0 pounds and you can't have negative 4.06 drinks. So how would we do the slope right here, Leo? I'm going to color code it while you answer the question. So I'm entering some color coding here to help with identifying what is what. The slope. Little color coding to help. For each 1 unit increase in what, we expect what to increase or decrease by this. And so all the color coding here to help out with where to find stuff. Where the x is at in the equation, where the y is at. And once again, try to write this down. Write it down because that's going to help you say it, write it down, have it down to be like, this is how I interpret the slope. This is how I interpret the intercept. There are variations we will accept, but I usually create more of a structure so that people are more likely to get it right. So what would we have right here? For each 1 unit increase in x, we expect y to increase or decrease by b1 on average. For each 1 unit increase in weight, we expect drinks per week to... Careful. For each additional pound someone has, or for each 1 unit increase in someone's weight, which is in pounds, we expect their drinks a week to... And Leo, wait, double check. Double check over there, Leo. Increase. Positive coefficient. The reason increase is because there's a positive right there. And then last but not least, we have r squared, which I'll put the r squared on the screen here at the same time. R squared is the percent of variation y explained by the variation in x. So this is the r squared value. You times it by 100. So how would you interpret r squared here, Leo, to end off office hours? How would you interpret r squared? To end off office hours. So remember, we just need to know y and x. Blank percent of the variation in y is explained by x. Blank percent of the variation of y is explained by x. By the variation x. Woo! I say on not rushing that. Blank percent of the variation y is explained by the variation in x. Blank percent of the variation y is explained by the variation in x. $6.58 and then percent, just throw a percent on that. Of the variation in variation 6.58% of the variation in not weeks consumed, drinks consumed. explained by the variation in weight. 6.58% of the variation in drinks consumed is explained by the variation in weight. Does that make sense, Leo? 6.58% of the variation in drinks consumed a week is explained by the variation in weight. No, Leo, get some sleep, Leo. 1,000 points. Leo, don't worry. Leo, it's all about that practice. It's all about that. I'm tired too, man, and I feel you. I feel you, man. We got break coming up here soon. So just take a breather, take a break, drink some coffee. Leo, you got this. You got this. Don't worry. I'm just the rebel story of my life. No, I'm here to give you positive encouragement, Leo. You're doing a great job. And to everyone else who sat down and practiced this right now, shout outs to you. Make sure to know how to interpret it. Make sure you can do your interpretations. Last night's email, I mean it. I see a lot of people who say like the slope is this, and I'm like 0 points. I'm like, no. With that, we'll be back here a little bit. More office hours later. Bye for now. Bye, Leo.